Okay, so here we have our predictions in column W and the actual values of whether or not somebody is pregnant in column V. So in order to actually estimate what these coefficients should be up here to get our real model, we need to tell the algorithm when it's wrong and when it's right, and how much it's wrong and how much it's right. So we can think when we're doing, say, a linear regression, our prediction, say with one of these coefficients you can think of as like a slope of a line, and those are going to be our predictions, and then these dots here are the actual observations, and there's going to be a distance between the actual observation and our prediction. Now here we have a dichotomous, yes, no, are they pregnant, but a lot of times predictions are, we call those regression problems sometimes, even when the outcome is not between 0 and 1. It's some continuous variable that could be between 0 and 100, or 0 and whatever, or negative something and positive something. It could just be any continuous number. And in that case, you would end up visualizing it this way. So the observations would be the dots, and our prediction would be represented by the line here, the slope, and the error by these red lines here. And so you can see that some of these are negative errors and some are positive errors. So as we've done in the past, we're actually going to square them. So we just put equals here, and we say this value minus this value. So this is the difference between them, and we will square that so we get all positive numbers. Send that down the rows. And now we want to compute something called the sum of squared error. Sum of squared error. And we're going to actually put that sum of squared error over here. And you guessed it, the sum of the squared error is the sum of these squared errors here. So enter that. And we're ready to solve this model. Now, you may have noticed that I made a couple of errors here. So if I click over here on predictions, right, that's correct. But as soon as I go down to the second row, you can see that I'm not multiplying these. So I forgot to put in some dollar signs here. So let's go ahead and put in dollar signs for these rows here. B2 through U2, the 2's need to be constants. And then I can send that down the rows. And so let me just double check that. Yep, that looks correct. And then for the squared error, we've got a similar situation. So if I go down this way, yeah, actually that should all be correct now that I corrected the prediction or the linear combination. And the sum of squared errors should also then be correct. So let's go over to the solver. And you can see I've already got these values added in, but I'm going to go ahead and just add them in manually. So I'll delete these all, remove, delete. And so this is simple. We're just going to set our objective to minimize our error, our sum of squared error. We want to minimize that. That makes sense, right? And click enter. And then we want to find out our decisions are what values we should place on for these model coefficients. Click enter. So B2 through U2, we're going to change those variable cells, and we are going to add the constraint that those cells need to be, see here, they need to be less than or equal to +1, and then they also need to be greater than or equal to -1. And you may remember that the correlation coefficient was also between -1 and +1, and we're going to be able to interpret these coefficients. Oops, that did not turn out. Let me edit that. The correlation coefficient also was between -1 and +1, and we're going to be able to interpret these regression coefficients in a manner that's very similar to the correlation coefficient. Let me just edit this one because I messed it up. So we want to have B2 all the way through U2. And click add, Click cancel, and it looks like everything's ready to go. We're going to use the Evolutionary Solver, which, by the way, again, this is just for educational purposes. You would not normally use this algorithm to solve such a problem, but we will do it here because we're treating the solver sort of like the algorithm that we're going to use, and I'll show you later what algorithms would be available to you to use in real life. So click solve, and the solver will probably chug away at tinkering at what values these regression coefficients should be, and you can see everything's changing, and this will probably take a while, so I will come back when it's finished. Okay, so my solver finished, and it says it can't improve the current solution and all constraints are satisfied, so I'll click OK. And it was able to tinker around with these values here in row 2 until we got our sum of squared error minimized down to 141.54. Now, since we're using the evolutionary algorithm, your computer, if it's maybe a better computer than mine, maybe it's going to get a lower number here. And you can also see that our predictions still don't look like ones or zeros, but the idea here is that theoretically we can figure out what some sort of cutoff value is here, and if it's higher than such and such a number, then they will be tagged as likely to be pregnant, and if it's lower than such a number, they will be tagged as likely to not be pregnant. And the idea here is that these numbers here in row 2, that's literally our model. This is our regression model here that we've trained. And the idea is that we can use that to make predictions about people who we haven't seen before, people who aren't in these rows of data here, and to use them to predict whether or not people that we haven't seen before are pregnant. Now, right now, we don't have really any way of evaluating how good these numbers are doing at all. Like, we don't even know how good these numbers would do on people in our own data set right now. So, except for we do have this sort of individual level thing, but we need ways to aggregate that so we know the error, across all participants rather than just for each and every participant individually. So we'll do that in some upcoming videos.